Good evening to all. Sorry for the delay. Slight inconvenience caused by the sharing of the screen. So without wasting much time, we can start the session for today. Welcome to the first week tutorial session of NPTEL course Power Plant Engineering. So I'll be conducting tutorial sessions every week. So today is the first session where we will be discussing on a few topics, few introduction topics. So we can go into the details from or the much more deep concepts from the next week onwards. So my name is Ananthakrishnan. I'm a Ph.D. candidate from Department of Mechanical Engineering, IIT Delhi. So in this week, the main lectures will be a few recap of Rankine cycle and fossil fuel steam generator, and we'll see a few multiple choice questions and detailed numericals based on a few base concepts. Look into the first problem. So this is a numerical based on the power plant capacity, load capacity. Try to solve it. I'll also try to solve it and explain within another couple of minutes.
आदि कब डालना है सर? आदि कब डालना है सर? हाँ यार, आदि कब?
Okay, then if so, you can actually post the answer in the chat if you want. we can discuss on it. Yeah. The question is regarding the load that is encountered by a power plant. It's mentioned that the peak load on a power plant is 60 megawatt. The loads having maximum demands of 30 megawatt, 20 megawatt, 10 megawatt, and 40 megawatt are connected to the power plant. The power plant's capacity is 80 megawatt. That is the capacity of the turbine or of the electricity capacity that is produced by the power plant. And the annual load factor is 0.5. Estimate the average load on the power plant, the energy supplied per year, the demand factor, and the diversity factor. So it's straightforward. So one thing we should note in these kind of problems is that the peak load is given as 60 megawatt, but at the same time, it's mentioned that maximum demands loads having maximum demands of 30, 20, 10, and 14 are connected to the same power plant. So if you sum all these, it will be more than the peak demand. So the actual peak load will be always less than the sum of individual peak loads. So this is something that we need to always remember. So that's how we design all the systems, all the thermal systems. We do not take into account we do not take into account the sum of all the individual peaks. Rather, we calculate the maximum peak that it might encounter. In that way, the individual loads may not be at always be at their peak. It will be slightly lower than their peak. Yeah, you are right. So we can actually calculate the average load by using the load factor that is given. The answer is right. So the first question is that we need to calculate the average load on the power plant. So the peak load on the power plant is 60 megawatt, and at the same time, it's been given that annual load factor is 0.5. So the first part of the problem, we need to calculate the average load on the power plant. So the average load on the power plant will be equal to the load factor yeah, right. So the load factor multiplied by the peak load. So the peak load is mentioned as 60 watt and the load factor is 0.5. So therefore, the average load encountered by the power plant is 30 watt. The second part of the problem asks for the energy supplied per year.
Megawatt.
Uh, so I didn't hear. Did someone say something?
I said, sir, the 60 watt it is megawatt, so 30 megawatt will come.
Yeah, right, right. I'm sorry. Sorry. So how will you calculate the energy supplied per year? So energy is actually the power multiplied by the time. So in this case, it's 30 megawatt and time will be so right. So the usually we express this in terms of kilowatt hour. So we can actually write this energy in terms of kilowatt hour, in terms of units that we would have seen in our homes. We pay for units of electricity. So that could be considered as a kilowatt hour. There's a direct correlation. 30 megawatt and yeah, you are right. 8,760 hours in a day. So the answer will be 262.10 power 6 kilowatt hour. So that will be the energy supplied per hour. These are straightforward questions based on the standard formulas. And what will be the demand factor and the diversity factor in this case? So we have been given the individual loads, individual maximum demands of 30, 20, 10, and 40, and the peak power, demand of peak load of 60 megawatt. So we know that, right? Then we have to calculate the diversity factor as well as the demand factor. So, so in the case of these two are the crux of this problem. These two are the new concept that we might be encountering in this problem. So how will you calculate the demand factor and the diversity factor? It will be peak load by connected load. Yes. So it will be peak load by peak load by connected load. Demand factor. Sorry, you are not audible. You can type it in the chat box. Okay, so we can actually continue. Two important factors. One is demand factor, and the other one is diversity factor. So in the case of diversity factor, right? So the diversity factor, the diversity factor should be straightforward, as the name suggests. It takes into account the diversity of the demands as well as the peak demand or the maximum demand that is encountered. So in this case, diversity factor is equal to sum of individual maximum demands divided by the simultaneous maximum demand. So this is the maximum that the power plant encounters, that is 60 megawatt, and the individual maximums of the nodes that are connected to the power plant will be 30, 20, 10, and 14. So at a single time, you don't expect this to be the total load. 30, 20, 10, and 14 will be the maximum of individual loads, but you don't expect them to happen simultaneously. So simultaneously, some combination of these four might give the maximum demand to be 60 megawatt, and you do not expect in any other case the load to go past this 60 megawatt. So the diversity factor in this case is the individual load sum 30 plus 20 plus 10 plus 14 divided by 60. That is 1.23. So that is straightforward. That is diversity factor. coming to demand factor, that is also quite similar to diversity factor, but slightly different. So it takes into account the maximum demand, that is the denominator of the diversity factor, and takes the connected load. So demand factor is maximum demand divided by the connected load in this case. At that point in time, what will be the total load that is encountered? That is actually the reciprocal of the diversity factor in this case. So the maximum demand that the power plant encounters is 60 megawatt divided by connected load. That is the sum of the individual loads. So that will be 30 plus 20 plus 10 plus 40. That is 74. So the value will be 0.811. So this is actually the reciprocal of the diversity factor. Uh, yes, the diversity factor is always greater than, yes, the diversity factor will be always greater than 1. It actually represents the sum of individual maximum demands and the simultaneous maximum demand of the system. So the new denominator will be less than the individual maximum demands. So the lowest it can go will be 1. It should be greater than 1 in all the cases. Energy supplied per year. So we can calculate the energy supplied per year in different units. So I calculate it in terms of kilowatt hour. So since we know the load in terms of power, 30 megawatt, right? Load, average load. We just multiplied it with into time. So it's basically calculating. It's basically power into time. So power will be 30 megawatt, and you just multiply it with hour, and so this megawatt is 10 to the power 3 kilowatt. So I just rearrange to get the answer in terms of kilowatt. Where is a connected load? 80. Power plant's capacity is 80 megawatt. It has got nothing. The connected load is 30 plus 20 plus 10 plus 14. The production is 80 megawatt, but the maximum of the connected loads is 74 loads. So if no more questions on this particular this problem, we can move into the next question. Okay. So look into the second question. I'll try to solve within a minute. So have you tried to solve this problem? So the question says a boiler. This is a question on boiler, and we need to calculate the draft produced in terms of of water, the efficiency of the chimney, and the extra heat carried away by flue gases per kg of fuel. A boiler may have waste gases leaving the installation when artificial draft is used at 150 degrees Celsius. The natural draft chimney is 60-meter high. The hot gases within the chimney are at a temperature of 300 degrees Celsius, and the air requirement is 19 kilogram per kg of fuel burned. The atmospheric air is at 17 degrees Celsius temperature, and the mean specific heat of hot gases is 1 kilojoule per kilogram Kelvin. The calorific value of fuel burned is 32,604 kilojoule per kilogram. We need to determine the draft produced in of water, the efficiency of the chimney, and the extra heat carried away by flue gases per kg of fuel. So it's a question on chimney. So it's a straightforward one. we need to calculate the chimney efficiency, the draft, and the extra heat carried away by the flue gases. So has anyone done this? So first question, first part of the problem is that we need to calculate the draft produced in terms of of water. So what do you mean by draft in the first place? So the draft is actually
The pressure difference which is created by the chimney is called as draft.
Yeah. Yes. Yes. The draft is actually the pressure difference that drives the flow of flue gases uh, inside the chimney from bottom to upwards. So it can be based on the density difference. So that natural convection based. So that will be the natural chimney, the natural draft chimney. And if you use artificial some kind of a fans or blowers, that will be artificial draft. So we need the height of the chimney to be such that uh, if you are using a natural draft chimney, the height should be sufficiently high to create the temperature difference for the flue gases to rise upwards. So we need to actually determine the draft produced in terms of of water. So in the case of natural chimney, so this will be the height. So in this problem, that is 60 meters. And then the outside air temperature will be 17 degrees Celsius. So the air will be equal to 17 degrees Celsius. And the flue gases, the hot gases are present at a temperature of 300 degrees Celsius. So the gases will be at 300 degrees Celsius. So we need to calculate the draft, that is the pressure difference that is between the outside and inside of the chimney. Then using the height that is given in this problem, we can actually calculate the pressure difference that is created because of this height basically. Has anyone tried to solve this? So we can actually calculate if no one has solved it, then I'll try to solve this. The draft produced in mm of water is basically the pressure difference So basically, the could be written in terms of mm of water. So we can denote it by H water. So that is given by the formula into H 1 by T ambient minus m plus 1 divided by m into 1 by Tc. So the TA will be the ambient air 17 and TG will be 300. So in terms of this should be in terms of Kelvin scale. And this M is 19 kg. This M is basically the fuel to air ratio. So basically it is 19 kg. 19 kg per kg. Sorry, air to fuel ratio. So air requirement is 19 kg of air per kg of fuel. So this will be giving you an idea of the pressure difference that will be created based on the flue gas pressure at the bottom as well as the top. So at the bottom, it is 300 degrees Celsius, that is 573 Kelvin. And at the top, it will be the ambient temperature, that will be 17 degrees Celsius corresponding to 290 Kelvin. So just substitute those. So this will be air fuel ratio. And this will be the height of the chimney. So height of the chimney is 60 meters. Basically, that gives just substituting the values. So this is mass of air to mass of air plus fuel. So this will give the draft of or the pressure difference created within this chimney as 34.13 millimeters of water column. The second part, we need to calculate the efficiency of the chimney. How will we calculate the efficiency of the chimney?
Same we will apply in that artificial artificial chimney, and then we'll see what is that value, and then we will divide. Artificial chimney also, that height is 60.
How much it is coming?
My point is artificial chimney, we will calculate with the same formula, but height is same.
Height is the same. Yes.
So then the same formula is applied in artificial chimney also. Then we will take the ratio, that is efficiency.
Right. So how much the value is coming to?
So for the artificial, it is coming as 20.32. 20.32.
Okay.
Efficiency is 20.32 divided by 34.13.
Okay. So I'll try to solve it. No, I don't think it's right. So the value of TG is 300 degrees Celsius. So that will be 573 Kelvin.
So what is the answer?
Yeah, the answer should be somewhere around 34. Okay, then I'll try to solve it. So you have to compare between the artificial as well as the natural chimneys in this case in order to calculate the efficiency of the chimney. So in that the hot gases within the chimney are at a temperature of 300 degrees Celsius. So that will be 300 plus 273, that will give you the 573 Kelvin. That's why the gas temperature is 573 Kelvin. Okay, so the section B, you have to calculate the chimney efficiency. Chimney efficiency takes into account, it's a comparison between the natural chimney as well as the artificial chimney. So it's given as you need to the same formula that we have used in the previous case. The height, total height multiplied by n by n plus 1 of Tg by Ta minus of 1 into G divided by CPG into Tg minus of Tga. So for the artificial one, the enthalpy difference per mass could be written as Cp of the gas, flue gas, into Tg minus of Tga. So the Cp is given as specific heat of the flue gas is given as 1.0032, and then the actual temperature difference is given as T gas, flue gas minus of the waste gas that leaves the insulation when artificial draft is used is 150 degrees Celsius. So the maximum that it could the difference between these two will be 300 minus 150. So the hot gases within the chimney will be at 300, and when it leaves the installation, it will be at 150 degrees Celsius. So that could be considered as the input energy. So that could be written as CPG into TG minus TGA. So that will be the input, and how much will be converted in terms of the pressure difference in the chimney. So that could be represented by using this formula. So in this case, it will be H will be the height of the chimney insulation. So that is 60, and M is 19. That is air to fuel ratio. And TG will be same as the previous case, that is 573 Kelvin divided by air temperature. That will be 290 Kelvin minus 1 into G 9.81 divided by Cp flue gases specific heat, that will be equal to 1.0032 into 10 cube into 573 minus 423. So that is the air temperatures leaving the installation. So the hot gases within the chimney will be at a temperature of 300, but it leaves the chimney at 150 degrees Celsius. So that will be the energy input to the system. So efficiency will always be output divided by input. So that multiplied by the 10 cube for converting this kilojoule per kilogram Kelvin to the joule per kilogram Kelvin. So the chimney efficiency will be coming around 0.3431%. So this is kind of different from that you have mentioned. So that can be another way of describing the efficiency of the chimney. This is based on the input energy and how much it is being converted.
But if we apply same formula, if we apply same formula which is there in the above, then why cannot we use that same formula? Because that will not account the specific that heat and all.
Yes. So efficiency has to be defined in terms of input and output, right? So the input energy the input energy will be in terms of the flue gas temperature difference, right? So can you just type it in the chat box once?
So my point is that 1.032 into 10 to the power 3, that factor we have not accounted in natural draft.
Yeah, I'm sorry. So you meant this, right?
No. My point is this one. That specific heat, na 1.032. That factor we have not accounted in natural draft.
No, it's not accounted in. So this is actually the efficiency, right? So it has to be input versus output. So in the first case, we had to find the pressure difference, right? There we need not worry about the input energy, the total input energy, specific heat. It's just a pressure difference that we calculate in the first one. So here it's more like the energy transformation that we take into account in the chimney efficiency. So can you just post it in the group so that I can answer it? The value of CPG is given in the problem 1.0032. Yeah, so so we need to convert it into energy unit, right? So basically, the denominator is in terms of energy unit. That is mg m into c into delta t. So the numerator has also to be converted into the energy units. So initially in the first problem, we have calculated the height in terms of meter, right? So in order to convert that into the energy, we have to actually multiply it with mg, right? So the denominator we divided, we have an m, and the numerator m gets cancelled out, and there is one g remaining in the numerator. So height into g into m, that will be potential energy, and similarly on the bottom it will be mcp into delta t. 423, that is 150 degrees Celsius. That is the waste gas leaving the installation when artificial draft is used. That is at 150 degrees Celsius. It's an energy to energy conversion, right? So we have to multiply the height in terms of mm to g in order to get the potential energy. So what is the answer for the third part of the problem? The extra heat carried away by flue gases per kg of the fuel. So this is in terms of kilojoule per kilogram Kelvin. You need to multiply it by 10 cube to get in terms of joule per kilogram Kelvin. That's why the 10 cube. So basically that is a extra heat carried away by the fuel. So that will be equal to the denominator of the second problem basically. So straightforward one. That is the input kind of energy to the chimney efficiency. How will so this could be represented as 1 kg of fuel that it corresponds to 19 kg of air. So total m plus 1 into Cp of the gas multiplied by T gas minus TA. So this will be 300 degrees Celsius. So it will be 573 Kelvin. And this will be 150 degrees Celsius. That will be at 423 Kelvin. The numerator, the denominator of the previous. So Cp will be 1.0032. M will be 19. That will be 300.6 kilojoule per kg of fuel. So basically, it's a straightforward problem. It uses the formulas. We had calculated the draft produced in mm of water. So for that, we need to consider the temperatures of ambient air and the temperatures of the flue gas, that will be at 300 degrees Celsius, and the mass flow rate of the air as well as the fuel. And we convert that into of water column. So that gives the it in terms of 34.13 of water column. But if you notice in the second problem, I haven't used that H. This conversion factor of 353. In order to calculate the energy transformation, so that will be without taking the 353, we multiply by G, that will be giving the potential energy per mass. And the denominator will be the extra heat, the heat carried away by the flue gas, the flue gases per kg of fuel. So that is CPG into TG minus TGA. And the third part is just calculating that. That's it. So yeah, that is a conversion. So the first part, we have to convert the draft produced in terms of of water. So the height, we need to convert that into height of water. So basically, you equate the pressure differences. So normally, we represent one atmosphere to 10 meters of water column, right? Or 760 of mercury column. So the similar calculation. So the usually what happens is one atmosphere of atmospheric pressure, right? So that could be written as so the pressure will be 1.01325 into 10 power 5 Pascal. That could be written as rho of water into G multiplied by the height of water. Similarly, for mercury, it could be written as rho of mercury multiplied by G into height of the mercury column. So that gives the height of the water column or the mercury column corresponding to one ambient pressure, right? So just similar to that, we just use a conversion factor to convert this pressure in terms of the water column height. So that is the ratio of the densities between the water as well as the flue gases. This is not a general formula, just for the application of only this particular problem. So if that is the case, we can move to the next problem. Look into it. I'll try to solve it in a minute. Okay, so this is a numerical based on power plant. So it's not based on the Rankine cycle. So it's not a question based on the Rankine cycle, but we can actually use the principles of Rankine cycle slightly in this problem to get the answers. Uh, so I'll read through it first. A power plant producing 120 megawatt of electricity has steam condition at a boiler outlet as 100 bar 500 degrees Celsius and the condenser pressure is 0.1 bar. The boiler efficiency is 90%. The boiler consumes coal of calorific value 25.7 megajoule per kg. The feed water temperature at boiler inlet is 160 degrees Celsius. The steam generator has risers in the furnace wall 40-meter high and unheated downcomers. The quality at the top of the riser is 8% and a minimum exit velocity of mixture leaving the riser and entering the drum is required to be 2 meters per second. The risers have 60 mm outer diameter and 3 mm wall thickness. Neglecting any pressure drop and heat loss as well as a pump work, we need to estimate the steam generation rate, the fuel burning rate, the evaporation factor, the pressure head available for natural circulation, the circulation ratio, the number of risers required, and the heat absorption rate per unit projected area of the riser. So this will be something new because this is completely different with a lot of new terms that is involved in this particular problem. So before that, we just try to draw everything in on a Rankine cycle. So on a TS plane, so this will be the turbine expansion process. where the work will be produced. The peak point will be at 500 degrees Celsius and 100 bar. 500 degrees Celsius. So this will be at 100 bars. So this will be the boiling process where the heat input takes place, and this will be the work producing 1 to 2 expansion turbine expansion process, and condenser heat rejection will take place at 0.1 bar. So 0.1 bar is taken, 500 degrees Celsius, 100 bar. The boiler efficiency is 90%. So that is amount of heat transferred to the actual heat input in terms of the calorific value of the fuel. So the boiler consumes a coal of calorific value 25.7 megajoule per kilogram. The feed water temperature at the boiler is at 160 degrees Celsius. So this is a Rankine cycle that has steam and water as the refrigerant. So this will be 0.4 and this will be 0.3. That is a pump case. So in this case, the feed water temperature at the boiler inlet is 160 degrees Celsius. So we can assume that there is a particular point here at 0.5 where there will be the feed water that will be going inside at 160 degrees Celsius. So this actually reduces the amount of heat input, the power input or the heat input that is required, making it a bit more efficient. So the steam generator has risers in the furnace wall, 40-meter high and unheated downcomers. The quality at the top, so that has got something to do with the geometry of the boiler. It has got risers that has 40 meters high and unheated downcomers. The quality at the top of the riser is 88%, and a minimum exit velocity of the mixture leaving the riser and entering the drum is required to be 2 meters per second. So we'll see where we can apply these quantities in the problem while we discussing the particular part of the problem. The risers have 60 mm outer diameter and 3 mm wall thickness. The first part, we have to calculate the steam generation rate. So I'll give you a few input data that you will be requiring to solve this problem. Otherwise, we have to use a steam table corresponding to the properties for the state points. So I'm giving it straight away. So the enthalpy at particular point 1 is 3374.8 kilojoule per kilogram. The corresponding entropy is 6.6011 kilojoule per kilogram Kelvin. So since 1 to 2 we can assume it to be an isentropic process, though in reality it might not be. We can say that S2 is also that, and we can find the output of the turbine to be will be having a dryness fraction. So we can calculate the dryness fraction based on this entropy. So that will be equal to S fluid plus X at 0.2. That is a dryness fraction. That is the mass of vapor to the total mass of vapor plus mass of fluid or the liquid at that particular state point at 0.2. So if you go further ahead on this line, at this particular point, the dryness fraction will be 1, and to the extreme left, the dryness fraction will be 0, where only liquid will be present. So you can expect this to be between 0 and 1. And SFG, that is the delta SFG, the change in the entropy at that particular pressure 0.1. So we can, I'll give you this as well. So SF will be equal to 0.6479 corresponding to the fluid, the liquid state at pressure 0.1. Delta SFG will be 7.5055. So this, we can calculate the dryness fraction X2 will be equal to 0.7932. So this is crucial because within the vapor dome, we require at least two properties to define it. So temperature and the pressure are dependent on each other in the saturated dome. A constant pressure corresponds to constant temperature as well. So in order to establish the point where exactly it is located within the vapor dome, we need a third property, and that is the dryness fraction. So we calculate the dryness fraction as 0.7932. From that, we can calculate the enthalpy. Therefore, H2 will be equal to similar to the entropy calculation. We have to calculate it from the state points from the steam table. The values of this enthalpy of the state points from the steam table. So HF corresponds to the fluid saturated liquid enthalpy at 0.1 bar for water, and delta HFG will be the change in the enthalpy from state point the pure vapor to the pure liquid at 0.1 bar of water. So that will be 191.46 plus 0.7932 into 2393.29. So that will be 2089.82 kilojoule per kilogram. So that with that we get the enthalpy of 0.2. 0.3 straightforward, that is a fluid one. H3 will be equal to 191.46 kilojoule per kilogram. And so though this is a pump, the pump process that happens from 3 to 4, we can denote the work input to the Rankine cycle as specific volume into P4 minus P3. This is very negligible compared to the turbine work. Hence, we often neglect this value. So this could be written as H4 minus H3. And in the case, if we neglect the work, because the specific volume is very low and corresponding to the pressure, it will be very less. So if this can be approximated to 0, H4 can be approximated to H3. That is the enthalpy of the state point 4 can be approximated to enthalpy of state point 3. Then at state point 5, that is the input to the input to the boiler. We can say that I'll give you the enthalpy for that case as well. So H5 will be 6 at 100 bar and corresponding to the temperature of 160 degrees Celsius. So that will be 675.5 kilojoule per kilogram. So with this, we can calculate the first part of the problem, that is the steam generation rate. The steam generation rate has to have some kind of energy balance. So in this particular problem, it's mentioned that a power plant produces 120 megawatt of electricity. So this is in terms of power. If you know the enthalpy difference, we can calculate the mass flow rate of the steam, and that is nothing but since this is a closed loop, that is nothing but the mass of the steam or mass of the water which condenses in this process. for the cycle. So the first part, we have to calculate the steam generation rate that can be calculated using energy or the turbine work. Turbine work WT is equal to 120 megawatt. That will be equal to WS into H1 minus H2. We already know the value of H1 and H2. So WS give the returns 120 into 10 power 6 divided by H1 is 3374.8 minus H2 will be 2089 point 82 into that is kilojoule per kilogram. So we multiply by 10 cube to write everything in terms of joules. So the value of the steam generated in this process will be equal to 93.385 kilogram per second. So that is the mass flow rate of the steam or the condensed water in the loop. So that is the first part of the problem. The second one, we need to calculate the fuel burning rate. So the fuel burning rate could be again an energy balance. So in this particular problem, there is a parameter that is given. That is the boiler efficiency is 90%. We know the input calorific value of 25.7 and the change in enthalpy within the boiler. So using these two, we can calculate the fuel burning rate. This could be written as so in the boiler, the efficiency in terms of steam generation is given as 0.9. That is equal to the energy imparted onto the water. That is WF multiplied by that is WS multiplied by change in enthalpy H1 minus H5 divided by steam the fuel burning rate multiplied by the calorific value, that is 25,700 into 10 cube 25.7 megajoule per kilogram. So just substituting the values, this is 93.385 multiplied by H1 minus H2, the H1 minus H5, that is 3374.8 minus 675.5 divided by WF into same. So this is multiplied by 10 cube is also there on the numerator. So the value should come around therefore WF is equal to 10.5 898 kilogram per second. So that gives the fuel burning rate based on the energy balance in the boiler and the efficiency of steam generation we can get. And the third part, we need to calculate the evaporation factor. Evaporation factor is nothing but a term or it's a ratio given us the ratio of the steam generation rate to the fuel burning rate. That is the evaporation factor of a boiler or in case of a power plant cycle. This is the particular term that we use as a ratio between the steam generation rate and the fuel burning. So that is evaporation factor. That is 1.385. That is 8.57. So the fourth part that can be slightly tricky. We need to calculate the pressure head available for natural circulation. So this is in case of in the steam generation. It is mentioned that it has risers in the furnace wall 40-meter high. So the furnace wall is 40-meter high and there will be natural circulation. And just like the previous case, we have to consider the pressure head that is available for natural circulation. So basically water will be there and it will be having some quality at the top. And it's mentioned that the quality at the top of the riser is 8%, and the minimum exit velocity of the mixture leaving the riser and entering the drum is to be 2 meters per second. So we need to calculate everything accordingly in order to find the pressure difference in this case. So any pressure difference problem will be having rho, G, and H terms. So rho will be the density term, and G the gravity, and the height that is mentioned in the problem, that is 40-meter height. So 40 we know, G know, we need to calculate the density difference. If it is natural convection, there will be some density difference between the top and the bottom. The quality at the top of the riser is given 8%. So that is something that we could use to calculate the corresponding specific volume and the density at the top point. At the bottom, that will be pure fluid. But since this is a vertical, it's mentioned that it's a riser and it is vertical in nature, so its height is 40 meter. So we need to calculate the average density differences. Top will be at a single particular density, but the bottom also will be at a single density, but the pressure difference as it flows from the top, bottom to the top keeps on decreasing. So we need to calculate the average pressure difference in this case. So for that, the lower pressure or the lower points pressure has to be an average between the bottom point as well as the top point. So if you assume this is a vertical riser and the bottom will be F and the top will be the top. So as the gas or the water moves upwards, the pressure difference actually reduces. So it has to be, whenever we are calculating this particular term, it has to be an average. So the mean density could be written as rho top plus rho F divided by 2. And rho M will be the high pressure and rho M, high density, and correspondingly rho top, rho rho F will be rho F will be the pure fluid or the pure liquid at the bottom point. As it rises upwards, its density changes and the quality changes. The top point is given in this problem as this is having uh, an 8% quality. So you can expect this to be somewhere here. So in that case, we need to calculate the density at the top point using 8% quality. How will you calculate density? You calculate the specific volume at that particular pressure using this quality and take an inverse reciprocal of it. So the question says we have to calculate the pressure head available for natural circulation. So delta P is equal to G into height into the density difference. That is rho F minus rho M. Yes, this is not there in the video lectures. This is something new. So that is the session all about. Something we'll actually look into something very new about the courses. So there will be the first two questions are based on the video lectures or somewhat similar. This one is slightly different and it will give you a breadth of knowledge in this particular topic. So G is 9.8 and H is 40. It's given in the problem. The height of the furnace wall riser is 40 meters. And rho fluid, that is the density corresponding to pressure 100 bar and 0.5. Sorry, not 0.5. This particular point where the quality will be 0. Its density rho F will be equal to 1 by specific volume at that particular point. That will be equal to that will be equal to 688 kilogram per meter cube, and rho top will be equal to basically I told you rho F. You can't actually use this. You have to use in terms of specific volume and then take an inverse reciprocal of it. So nu top will be equal to nu fluid plus X into delta nu Fg at 100 bars. So this will come around. This is 0.08 and this will come around 0.002779. So using that, we can calculate rho top equal to 359.8 kilogram per meter cube. So rho M will be equal to rho top plus rho F divided by 2. So that's equal to 523.9 kilogram per meter cube. So rho F minus rho M will be equal to 688 minus 523.9, and that is the pressure difference available for natural circulation. So that is equal to 64.327 Pascal, kilopascal. That is the pressure head available for natural circulation. And then we need to calculate circulation ratio. That might also be a new term for you. The circulation ratio is actually the reciprocal of the quality at the exit of the riser. So circulation ratio is the reciprocal or the inverse of dryness fraction at the top. Just given the problem, the dryness fraction of the quality at the top is 8%. So it will be 1 divided by 0.08. That is 12.5. So straightforward one. This is just a terminology that is used in this part, these kind of problems. And then coming to the last couple of problems, the number of risers required and the heat absorption rate per unit projected area of the riser. So it's mentioned that the risers have a 60 millimeter outer diameter and 3 mm wall thickness. And that means the inner diameter or the cross-sectional diameter through which the water flows is 54 mm, and the velocity is given in the problem as 2 meter per second at the top point. So if you consider the top point, then you have to take the density of the top point as well. So we can that is just could be the mass flow rate of the water that flows through the riser will be equal to rho into cross-sectional area of the riser multiplied by the velocity. And at the top, it will be having a quality of 0.08. So quality or basically the dryness fraction will give you the actual mass, the total mass flow rate will be a combination of the riser as well as the total combination will be at this particular point of it will be in the state, it will be having two states, both a vapor as well as a liquid coexist. So we have to actually calculate the steam formation rate. The steam formation rate could be written as the mass flow rate, total mass flow rate multiplied by the quality. So that's basically takes into account the dryness fraction as well as the velocity, cross-sectional area, and the density at the top point. If you are taking the top point, you have to take all the properties at the top point to be consistent. So we know the actual steam generation rate. So so this will give the steam generation per a single riser, per single riser. So using these two, we can calculate the number of risers required. So the number of risers required for steam generation will be equal to the WS, that is steam generation rate, WS per riser. So this is 93. It's already be calculated in the first part of this problem. And this area, the volume flow rate multiplied with the density at the top point into the quality will give the steam generation per riser. So that is pi by 4 into inner diameter squared. So this is equal to d outer minus 2 times thickness, wall thickness into rho at the top and the velocity of the steam at the top or the water steam mixture at the top multiplied by the quality. So this will be 0.08. and the velocity at the top point is 2 meters per second. Density at the top will be equal to 359.8. That is a reciprocal of the specific volume at the top. Specific volume we have calculated using the quality as well as the fluid specific volume and the change in the specific volume at the pressure. At the pressure at the top pressure, that is 100 bars. So inner diameter is equal to outer diameter minus 2 times thickness. This will be 54 millimeters. So that is 54 into 10 power minus 3 meters. So this already simplifying and doing the calculation, we get the number of risers equal to 712. So the number of risers required for steam generation is equal to 712. It's a straightforward one. And the last part of the problem, we have to calculate the heat absorption rate per unit projected area of the riser. So how will you calculate the projected area of a riser?
It is a four wall of a boiler.
Yes, please. So in this case, this is a phase change process. So once the fluid actually moves from bottom to top, a portion of that will be converted. A portion of the liquid will be converted into vapor. So basically, it is mass of water that is converted into steam multiplied by the enthalpy of vaporization. That will be the heat transferred in this process. So once it completes the process, it will be total mass flow rate of the steam that is there in the steam generated multiplied by the HFC of this process. So in a single riser, there is an inner diameter and there is an outer diameter. The projected area is always, this is a cylinder basically. The projected area should be written as the, so basically a 2D drawing of a cylinder when you look from the top might look like this. Basically that is a projected area, not the cross-sectional area. So that is d outside, d out minus into h. So that will be the projected area. So projected area will be equal to d0 into h. And heat absorption rate per unit area of the riser, a single riser. So that is equal to the mass of steam or the steam per riser into HFC. So that is the energy transfer during the phase change process in a single riser. So it is not the entire flow rate of the steam, but rather the flow rate of the steam per riser. So it requires 712 risers to actually generate the entire steam. So a single riser will be producing the quantity that is 0.131. So 0.131 into HFG, that is enthalpy of vaporization corresponding to 100 bar. So difference between this point and this point, not 1 and 5, this point and this point at 100 bars. That is, I'll give you that. So that value is 19.8 kilojoule per kilogram. And the area will be equal to outer diameter into height. So this is 0.06 meters. That is, it's given in the problem. The outer diameter is 60 mm, that is 0.06 meters, and height is 40 meters. So that the value will be equal to 72.4 kilowatt per meter square. So that's pretty straightforward. So this problem actually introduced a few new names for you. Nomenclature wise, this will be new names. So physically, that will be very similar to what you have studied previously as well. So here in this particular problem, this is based on Rankine cycle. We calculated initially the steam generation rate using the turbine work and the enthalpy change in the process 1 to 2. For the fuel burning rate, we calculated based on the efficiency of the boiler, that is 90%, and the calorific value of the steam. So we have calculated the steam generation from the first part of the problem, and the only unknown that is remaining in that particular problem is the steam, is the fuel consumption. So that we can calculate using this energy balance or the fuel efficiency equation. The calorific value and the boiler efficiency. And then the evaporation factor is a term point to actually refer to the ratio of steam generation rate and the fuel consumption rate. And fourth part of the problem, we had to calculate the pressure head available for natural circulation in the riser. So it's basically rho g h, but this happens by natural circulation, natural convection process. So that definitely in that case, we have to calculate it based on a density difference. So we can calculate the bottom point density that will be at a pure liquid condition at 100 bar, and top point will be having a quality of 0.08. That will be a mixture of liquid as well as gas. So we can calculate the density at the point, specific volume basically. The actual flow in the case of vertical columns, we have to consider the pressure difference in terms of density difference, and we use the bottom point density, and the top point density is actually the mean between the top and the bottom point. So that gives the pressure head available for natural circulation. And then circulation ratio is also a new term for you. It is a reciprocal of the dryness fraction at the top. It's already given. So the new terms in this particular problem are the evaporation factor and the circulation ratio. And basically the others, the number of risers required, you can calculate based on the total steam generation rate and the steam generation rate per rise. And the heat absorption rate is also quite similar. It's mentioned unit projected area of the riser. You have to calculate the mass flow rate or the mass which is converted from liquid to the vapor in a single riser and multiply it by the enthalpy of vaporization. That will be the total energy transfer that will happen within a single riser, and you have to divide it by the projected area of the riser, that is outer diameter into height of the riser. So that completes this problem. Any doubts? No doubts are there, then we can actually move into the multiple choice question. The efficiency of the Rankine cycle is often improved by an increase in the boiler pressure. Select the correct statement regarding the effects of increase in boiler pressure on the Rankine cycle. Just look into the 4 options and say which is the right answer. Yeah, right. Option A is right. Yes, yes, right. So what happens when we increase the boiler pressure? So boiler pressure is the top point pressure. So what happens when we increase the boiler pressure, keeping every other parameter same? So one of the most important things that we need to remember is that uh, the efficiency of a cycle could be written as, in a basic sense, when we try to bring an equivalence to that of the Carnot efficiency, could be written as 1 minus of T low by T high of So the efficiency could be written as 1 minus of TL divided by T high, where the TL is the mean temperature of heat rejection and T high is the mean temperature of heat addition. So basically sink and source terms. So this may not be the same. TH as a high point temperature in the boiler will not be remaining the constant, will not be remaining in constant. So we have to calculate an average temperature of heat addition. Similarly, for the condenser, though so in this case, it is inside the vapor dome. Therefore, the condenser temperatures remain a constant. So therefore, TL will be the condenser temperature. T high you have to calculate a Once we increase the boiler or boiler pressure, the temperature of once we increase the boiler temperature, once we increase the boiler pressure, so this actually the heat addition curve goes upwards. This means that the average temperature of heat addition increases. So once the average temperature of the heat addition increases, so the whole term decreases and the efficiency increases. So this is right and this is right. And what about the vapor quality at the turbine exit? So basically, we are only increasing the vapor. We are only increasing the boiler pressure, right? So keeping every other parameter constant. That means that the temperature exit of the boiler should remain the same as that of the. Yes, it should. It should. So basically, going by this analysis, right? 1 minus TL divided by TH, it should increase. Uh, yes, going by this analysis, yes. So then what about the vapor quality? So the temperature at this particular point uh, should be the same as that of the first point's temperature. So the heat addition process ends at this particular point. So once it does ends at this point rather than this point, and it is an isentropic expansion in the turbine, it shifted towards the left. So once it shifts towards the left, the dryness fraction at the exit of the turbine reduces. So the vapor quality reduces and it will be filled with the steam will be filled with the more content of the liquid. So the vapor quality at the turbine exit decreases. So this is right. But in order to avoid that, there will be superheating or reheating. The superheating can be extended or reheating process can be there. That will actually shift the curve towards the right to improve the quality, vapor quality at the exit. Uh, that completes the session for today. In today's lecture, we have seen a few numericals and one multiple choice question. Numericals are kind of slightly widespread. So we are seeing one based on the, yeah, it should be available. We will upload that and it will be mailed to you as well. So it I have already recorded the lecture. So we will be uploading that and the NPTEL authorities will be sharing an Excel sheet with you with all the links of the YouTube lectures. So we'll be uploading that in the YouTube. So the YouTube lectures will be available. The links of the YouTube lectures will be available in that Excel sheet. And also the slides will be shared to you on a Google Drive. So you need not worry about that. So yes. Yeah, so we have seen a few questions, and the first one was based on the demand and the peak load that is present on the power plant. So we have seen that diversity happens. So the peak doesn't get added up. So the actual peak demand of a power plant will be lower than that of the demand, lower than the sum of the individual maximums. So that is a diversity factor. Demand factor is actually kind of a reciprocal. So the maximum demand encountered by a power plant towards a connected load in this case. Then we saw a problem on the natural and artificial draft of chimney, where we had calculated the draft produced in of water, the efficiency of the chimney based on the input energy, and the potential energy, or the difference in the flue gases energy, and difference in the flue gas potential energy from the bottom to the top, and then the extra heat carried away by the flue gases as well. And in the third one, we have seen a Rankine cycle based problem, and seen a few quite new terms that we have discussed. Finally, we have seen a multiple choice question for this session. So in the next week, we'll see. So in this week, I haven't actually discussed about the different types of the boilers and the mountings and accessories, and the boiler performances. In the next week, I'll actually discuss quite a few on the types of boilers, water tube boilers, fire tube boilers, and the different various types. Wilcox boiler, and we will see a few more on that in the next week, and also based on the second week's lectures, a few problems as well. So if you have any doubts, you can post that in the course website forum that is available. So the course TAs will be answering that, and we'll meet next week at the same time. Thank you.
Thank you, sir.
Thank you.
Hello.